Okay, recording. All right. Okay, so sorry about that. So we use mass conservation to write down the essentially the incompressibility constraints. Then we wrote down momentum conservation A equals F over n. That's how you write F equals ma if you're a professional scientist. And because you know what the forces are, and they give you the acceleration. Knowing F equals ma is putting the cart before the horse. The Hi there. The internet went down in our building, so sorry about that. All right, so I'm going to switch on to recording, and it thinks it is recording. Okay, well, that's great. Okay, let's put that down. Okay, I'm sharing. I'm not showing my screen. And it is still recording. Okay. Johnny, can you see my screen? Can you hear me? Why don't I hear you?
I can see the screen and I can hear you.
Great, and it's recording, right?
Yes.
And there was one other person who was on. I guess she just dropped off because she was probably affected by the whatever went down. Okay, so we're recording, so we'll just keep going. Okay, I remembered to Zoom, start screen, record. Okay, all right. So what we want to do is we want to try to explain convection patterns, meso soup. So what we did was we first of all took the uniform state where there is no fluid velocity. We solved for the temperature profile. It's just a little what the hydrostatic pressure is. And then what is our goal? Our goal is this. We're going to write down the temperature, the pressure, the velocity, and the density as their steady state uniform values plus a perturbation. And then we're going to write down equations of motion for that perturbation. So that is our goal. So let's get started with that. And I want to I'm going to follow what is section 7.3 in my book. So let me just make a comment. So the strategy that we're pursuing is look at the steady state and look at its susceptibility. And we did the same thing in Landau theory, but I didn't tell you that. So let me explain to you why I say that. So in Landau theory, we had the following situation. Here was our order parameter. Here was the potential for that order parameter. And we looked at the system where it starts off in a state with no order, so psi is equal to 0, and then we change a parameter, and now the system looks like this. And so what we can think of is imagine that you had started out here at psi is equal to 0, and now we had suddenly changed the temperature so that the system went from the state T greater than Tc to the state T less than Tc. Then what's going to happen is that this psi is equal to 0 goes from being a stable equilibrium to an unstable one. And you can see that here, if we now have the T less than Tc and we start at psi equals 0 plus a little bit of noise, what will happen is the system, let's suppose the noise is pushed slightly in this direction, then the system will go down this well and eventually get to this equilibrium position down here. So this psi will go from stable to an unstable equilibrium, and the consequences of that is that any small fluctuation will cause psi is equal to some non-zero value. And the thing that measured this was the susceptibility. If we look at the susceptibility, chi is equal to, say, dm by dh in the case of a magnet, this then becomes negative at m equals 0 for t less than tc. And this negativeness means that the m equals 0 state is unstable. Now, what we're going to do here, the main difference though, is here we're going to look at this dynamically. Whereas before, what we did was just look at signatures of instability in this state, in the equilibrium state. So we can see that that m equals 0 is unstable for t less than tc without having to perturb the system. We just look at the susceptibility, and the fact that it's negative tells us that the system will then become unstable. Now, let's go back to Landau theory and remind ourselves what its form was. So the form of it was grad psi squared, and then this potential, which I've called v of psi. So that's the potential, and so we can ask what happens. We can do the thought experiment about what happens when we make a small perturbation away from psi equal to 0. So what happens is that initially the psi moves away from psi equal 0. And if we only look at the dynamics, that's the only thing that we can see. So that's the first thing. So we're going to capture this initial dynamics by what I'm showing you next is linear stability theory. So that's what happened initially. Now we know that what actually happens is as time goes to infinity, psi approaches the minimum I didn't say that v of psi is equal to a half a psi squared plus 1/4 b psi to the 4th, and that minimum is equal to what? Psi is minus a over b square rooted, right? Maybe this factors it too. And so what's going to happen is that the psi later is restabilized around this new minimum. And the thing that does the restabilization is the nonlinearities. So what are the nonlinearities in this particular case? Well, of course, the whole potential is nonlinear, but when I look at the equation of state, that comes from looking at dv by d psi is equal to 0. And if I have in here an external potential h psi, then that will give me that h is equal to a psi plus b psi cubed. Okay, so when I talk about the nonlinearities, what I mean is this is the nonlinearity. So that nonlinearity comes from the quartic term in the potential. And so that's the thing that restabilizes it. And how do I know it restabilizes it? Well, it's because the coefficient of the quartic term is a thing that comes in here to the equilibrium value. So this notion of linear instability about the state that is now unstable, and then the restabilization around the new minimum. We understand that picture in equilibrium statistical mechanics, but it's not. But what we're going to do now is look at it in a non-equilibrium system. So the next thing we're going to do is we're going to look at this picture of an initially unstable state evolving to an eventually restabilized state. And we're going to look at this dynamically, because we are far from equilibrium. And so we can't use Landau theory or Gaussian distribution or anything like that. Okay, so let's go ahead and do that. So what we're going to do, the other quick question is a quick.
Yes, maybe just a clarification by this quartic term.
Yes.
Sign the third. Do you mean so I'm looking at it as this state travels down from the linear instability into this as well?
Yes.
And so are we already assuming that it's going to overshoot and oscillate as like?
We're agnostic about that.
Okay.
The only point is that the quadratic term, if I only have the quadratic term, this would go downhill, yes, and the minimum would be a minus.
Right.
Okay, so that's no use. So there's a quartic term, which is nonlinear in the equation of state or in the dynamical equation, that then restabilizes, causes this to go up, and causes there to be a new state which the system can be stabilizing, which is the state of spontaneous energy.
But we're not saying anything about dissipation, right?
No, I didn't.
Exactly. That's all.
Right now, we've got no equations of motion. That's just an equilibrium picture, which says nothing about the dynamics. Okay. So any other questions? I've got a lot to get through today, so keep it short.
Quick question.
Like, yeah.
What is the significance of X?
What is the significance of what?
The X. Like if you find X to be like the V divided by psi. Like
what is A? What is the significance of what?
In the next slide, like the H there, like that's just the derivative of the potential.
What is the significance of H? Yeah. External magnetic field.
Oh, I see. Oh, it's the extra electron.
Okay. All right. Okay, right. So now we're going to do the calculation. So I'm not going to do the whole thing for you because it's quite complicated. So it's in my notes. So what we do is we say that T is the equilibrium value that we found last time. We say that rho is the equilibrium value that we found last time plus a perturbation. We say that the pressure is the equilibrium value that we found last time plus a perturbation. And we say that U is equal to 0, the equilibrium value we found last time, plus a perturbation. And then what we're going to do is we're going to take this, plug into the equations of motion, and we're going to work to linear order in the perturbations. When I talk about perturbations, I mean these quantities here, the perturbations about the steady state. Okay, so let me write down what those equations are. So if I do that, then I get the following equations. Rho 1 is minus alpha rho bar T1, div of U1 is equal to 0, rho naught of Z du1 by dt is equal to minus grad P1 plus eta del squared U1 plus rho 1 G, it's a 1, and this is a vector, and dt1 by dt plus W1, and I'll say what W is in a minute, dt naught by dz is equal to kappa del squared T1. So those are the equations, and I've written that the perturbation U is equal to U1 V1 W1. So any velocity field has components in the x, y, and z directions, U, V, W. Okay, so those are the equations you get, and you can see that these are linear coupled partial differential equations. Okay, so awful, right? So let's just talk about the basic idea then of linear stability analysis.
What is rho bar?
The rho bar, if you look at the equation of state, rho bar was the reference density.
Yes.
Okay. So here's now the basic idea. So I'm going to spend a bit of time on the basic idea since that's the main thing that I want you to know about. So in general, let's suppose that I have a bunch of variables which I'll call psi of x and t. So psi can be a scalar, could be a vector, could be a tensor, doesn't matter. I don't care what it is. It obeys some equation of motion. So there's some nonlinear operator acting on psi, and that nonlinear operator can include nonlinear polynomial terms, derivatives, all sorts of things like this. Okay, so this is some nonlinear operator. And then if I want to look at the steady state, so that's the state d psi by dt is equal to 0, and so therefore we'll call that psi naught. So therefore the nonlinear operator of psi naught of x and t is equal to 0. So that's the steady state. So now what we do is we do perturbation theory. So I'm going to write that psi is equal to psi naught plus psi 1, and psi 1, of course, is a function of x and t. And then the equation of motion of psi 1 is d by dt of psi 1 plus the nonlinear operator psi naught plus psi 1 is equal to 0. And now what I'm going to do is I'm going to do an expansion of this nonlinear operator. So technically a mathematician will call it a Fréchet derivative or something like this, but I'll just write it symbolically. This is just d psi by dt plus dn by d psi evaluated at the function psi naught of x operating on the function psi 1 of x and t. And then this is equal to 0, and there's of course higher order terms which we are going to neglect, and we're neglecting those because what we're doing is linear stability analysis. So from the point of view of a linear stability analysis, I have the equation d psi 1 by dt is equal to L psi 1 of x and t, where L is defined to be dn by d psi evaluated at psi naught of x. And in general, psi naught of x may be a spatially dependent function. So this may be a function that is spatially dependent. This may not just be a simple derivative operator. It may be an operator, like if I'm linearizing about a state that has a pattern, then that operator will be a very complicated differential operator. Okay, so that's the sort of that's the setup. So what do we mean by stability? So what we do is we say, let's do a Fourier decomposition of psi 1. So I'm going to, you can think of that as saying let's put in psi1 equals e to the I k dot x plus omega t. And in general, omega will be a function of k. So it'll have a dispersion relation, which it'll be our prerogative to try and identify. So we will plug that in. And so therefore what we get then is that omega of k psi 1 is equal to L psi 1. Okay, so L is a differential operator, possibly spatially dependent. And so what we have then is an eigenvalue problem, just like the ones that you solve in quantum mechanics. But the problem is that L is not necessarily Hermitian. May not even be symmetric. And what else? Omega of k is called the dispersion relation. It is basically the eigenvalue spectrum. Of L, of the linear operator L, and you also call this the growth rate. And why do we call it the growth rate? Well, if you look at this term over here, this says that if I make a perturbation, it has an amplitude A, and that amplitude grows as e to the omega t. So if I know omega, then I know whether the amplitude is going to grow or decay. So now let's have a look at the possible scenarios that we might have with this kind of situation. So the first scenario is the following. First one I'm going to write down is that the real part of omega of k is negative. And that's true for all values of k. So this means that any Fourier component of the perturbation will exponentially decay in amplitude. And so if that is true, then we say, let's use a different color, that means that we say that the state we are perturbing about, which in this case is the state that we called psi naught of x, is linearly stable. So that's the first scenario. Okay. There's a second scenario that can happen. So what may happen is that the real part of omega of k may be greater than 0 in some band of wave vectors. Let me write it as something like this. So what that means is that in this case, Fourier components in this band will grow exponentially. What will happen when they grow exponentially? Well, their amplitude will increase. And once it is non-infinitesimal, then we are out of the regime of linear stability analysis. And the reason is that the equations of motion that we're looking at are the linearized equations of motion. And since they're the linearized equations of motion, we're assuming that everything is small. If some of the things, some of the quantities are growing exponentially in some wave number range, they'll all be growing exponentially, then they'll eventually get out of the regime where we can make this small amplitude approximation. And then what will happen to them? Well, in our hearts, we know that eventually they will become restabilized in some way, but they're restabilized by nonlinearities. And we've thrown away the nonlinearities. So this analysis can't tell us anything beyond its breakdown. So all we can say in this particular case. So in this regime, the order psi1 squared neglect is not justified. We've the nonlinearities that restabilize the system are not included. And so all we can say is the state that we started with, psi naught, all we can say is that it is linearly unstable. But we can't say what it's unstable towards. We can't say to what it is unstable. So as an example, a solid state physics example, so the condensed matter analog might be start off with a normal metal. So a normal metal might be, say, free electrons. You learned about free electrons on your mother's knee. When you go to graduate school, you learn about Fermi liquids. So we'll call this thing a Fermi liquid. It's a Fermi liquid of quasi-particles, which are electronic degrees of freedom, which are create quasi-particles in the same way that we talked about in this course in terms of Bose-Einstein condensates. So we have excitations that are electron-like, they're fermions, and they describe a normal metal. And if we take such a normal metal and we subject it to electron-phonon interactions, what we can see is that that tells us that the Fermi liquid is unstable. To certain types of interactions. But you can't say what it's unstable towards. So people already knew Fermi liquids were unstable in the middle 1950s. But it wasn't until the Bardian and Cooper-Schrieffer theory wrote down the wave function of the superconducting state that people knew what it's unstable towards. Now, the way we did superconductivity, we didn't do it in the class, but I told you that one can do it in the same way that we did Bose-Einstein condensates. You use the Broglie-Lebov method, you can literally derive the wave function, and so you can figure out what it's unstable to. You can derive both sides of the phase diagram. So we have a phase diagram where you have some attractive interaction. So here you have Fermi liquid, and here you have superconductor. And all you can tell is that this is unstable, and you need BCS theory to identify what it's unstable towards.
Because it started by calculating like susceptibilities or something.
So you need BCS theory. So in a sense, what the BCS theory is doing is the BCS theory or equivalent is telling you what are the nonlinearities that destabilize a Fermi liquid into a coherent quantum condensed state. So this is exactly analogous to what we've done before. So again, in condensed matter, we do know how to. We can include the nonlinearities relatively easily, and so these are the two main cases: linear stability and linear instability. I'll come back to your question in a second. Okay. In addition, there's one other state, which is that the real part of omega and k might be less than or equal to 0. And when it's equal to 0, that means that there exist marginal states. And if they have real omega equals 0, then that means you need higher order terms. Because linear stability analysis is not going to be able to tell you. So the last thing I want to say about this is that which scenario you have depends on the control parameters. They may be several. We'll call them epsilon here. That's what we talked about last time. And so in our convection experiment, that might be the temperature difference between the bottom and the top. Okay. So next thing I'm going to do is I'm going to draw these scenarios that I've outlined for you as a function of epsilon. Professor, I'll take your question.
Yeah, I was just wondering, like you said that one knew that's probably pretty unstable.
Yeah.
Before we knew about it.
Yeah.
Like, but did we know the order parameter?
Didn't need to know the order parameter. We just simply looked at the poles of the green functions. Okay. So go and ask whoever teaches solid state physics, and they'll tell you about that. Or you can ask me afterwards. Okay. So okay, so now let's sketch these scenarios. So the first one I'm going to draw. So in all of these, I'm going to be drawing omega of k versus k. But when I write down omega of k, I want you to understand that it's really the real part of it. Okay, because I do just to save writing all that. Okay, so let's have a look at what these scenarios look like. So this is the scenario, the first one. Here's the eigenvalue spectrum of the operator L, and this is a case where epsilon is less than the critical point, less than the critical value. So all the modes have real part that is negative, so they all decay. Then case 2, well, actually, I'll draw this in. I'll draw this as case margin. So here is the case where epsilon equals the critical value. So one of the modes has just touched the real, the omega equals 0 axis. And then here's the last case. So this is epsilon greater than epsilon c. And you can see here is K1, here is K2, here might be a Kc. And in this particular case, in this range, these are all unstable. And over here, these are stable and stable over here. So what we have is we have a band of unstable wave vectors. This would be a really terrible name for a pop group.
I think it would be pretty cool, actually.
Well, my band was called the Renormalization Group. Okay, if we have that the size of this band K2 minus K1, if that is much less than K0, then that means that we are near threshold. And only a few modes are unstable. And this we can analyze. This we can analyze Kc. Thanks. This we can analyze by weakly nonlinear analysis. And I'll try to talk about that. Okay, so that's what happens. Now we can ask ourselves the following question. If a pattern emerges, what is going to be the scale of any pattern that emerges? And so the answer is very simple. Omega is the growth rate of a perturbation. I've got a band of modes with different wave numbers that are unstable. So these will all grow exponentially. If I wait a long time, so all of these modes are growing exponentially, which mode will have grown the most after some period of time?
The one with the largest growth rate.
Right. So the K value with the largest omega of K will grow the fastest. And that means that we expect that patterns that emerge will have scale, wavelength, going something like 2 pi over, let's say, K0, something like that. Okay, so that's the basic idea. Anybody have any questions about this basic idea? Because what I'm going to do is if it's quick.
It's why, I don't quite follow why, I think I remember this last year, but why K2 minus K1, much less than KC? If I'm looking at this plot, these plots on the left, I kind of don't see.
Right.
I mean, you should just see
Well,
that.
remember that these modes are discrete. Okay, so if I've got a million modes in here, and I've got a whole million modes that I have to fully analyze and study. If I've got, say, the fastest growing mode and maybe one other mode, that's much easier to study. I can write down the questions for it. That's it. Okay.
Yeah, no problem.
Okay, so then our task is to work out what is the result of this analysis for convection. And I'm just going to refer you to ESM 7.3.1 and 7.3.2. And I will write down, I'm not going to derive those equations, so you can look at them in the book. I'm just going to write down what the answer is. So if anybody wants to know this, you can ask me privately. So what you end up doing is we have our fluid that looks like this. So that's cold. This is hot. And what we're going to look for is an equation for the vertical velocity field W1 as a function of z and time, and actually I want to write that differently, as a function of x, y, and z and time. So that's what we can solve for. And if you follow the calculation, what we can do is we can beat it down into the following form. W1 of x and t is some function capital W of z times some function of x and y in the xy plane. There's z. There's x and y. And then it goes as e to the omega t. And the function d2 by dx squared plus d2 by dy squared of f of x and y is equal to minus a squared f, where a is an eigenvalue that we'll find out, and dz 4 w minus 2a squared plus w over nu, that's the viscosity, d squared w is equal to 0. So that turns out to be the equation of motion, and actually that's not the equation of motion. I'm going to erase this. Ignore that, completely wrong. The boundary condition. Okay, the equation of motion is this. I'm going to say d is equal to d by dz. So you get nu d squared minus a squared minus omega times kappa d squared minus a squared minus omega acting on d squared minus a squared w is equal to alpha g t naught prime by dz times a squared w. So this is a horrible mess, okay? This is a horrible linear differential operator with unknowns a and omega, and those, it's a sixth order equation, and so those unknowns have plus boundary conditions. And I'm not going to write down what the boundary conditions are because they're complicated.
What's that third term in the middle? D squared minus a squared minus
W.
W.
Well, it is because because whatever this app is messed up. Okay. Where is what?
So just after the W. I'm just confused about the continuity from that.
The multiple.
Next
Well,
one.
this is
Times
omega
and times.
times.
Like on the new line.
Yeah.
Yeah,
This goes into this.
And sorry, that's an omega, not a W.
Here's an omega.
Okay.
Okay, don't worry about it.
Okay.
Okay, you're not going to solve it. Okay, it's in my notes. Okay, so what you do is really simplify the boundary conditions. And when you simplify the boundary conditions, what you end up with is the following. There's a quantity which I'm going to define to be a squared, which is a squared plus n squared pi squared over d squared. D is that separation, and the eigenvalues, which is the only thing we really care about, turn out to be -1/2 nu plus kappa a star squared plus or minus the square root of some awful thing to 1/2 power, and it doesn't really matter what it is. Okay, so it's some awful mess. So what you need to know is whether omega, or its real part, is greater than 0 or less than 0 as a function of k, and the k vector is n pi over d, and that n is the n that comes in over here, and then as a function of k, and then also a itself. So the so you've got anyway, so you have to solve this algebraic problem, and then what you find is exactly like we talked about before. As a function of the wave number in the z direction, a times d, you look at omega, and what you obtain is a curve, a series of curves that look like this, and what I want to jump ahead is to tell you about the Rayleigh number, Prandtl number. So there are two dimensionless numbers that control the phase diagram. So one of these is called the Prandtl number, which is nu over kappa. Remember, last time we talked about the variables that prevent convection occurring. One was the viscosity of the fluid, one was the thermal conductivity. So this is the ratio of the two variables, the viscosity and thermal conductivity, that prevent thermal convection occurring. Okay, then there is the Rayleigh number. And the Rayleigh number has in its denominator nu times kappa. And then here it has alpha, the thermal expansion. It has the gravitational field, because that's the buoyancy. It has the temperature, and it has the spacing, and it has the spacing to the cube power. Okay, so that just turns out to be what it is from the analysis. So the Rayleigh number, when Rayleigh number is greater than Rayleigh critical, which is somewhere around 1700, I've forgotten the exact number, this is the critical value for Rayleigh number greater than Rayleigh critical. That means you get convection. And so linear stability analysis, this calculation, which I've only sketched and told you about, enables you to find what are the variables that control the instability, and it tells you when the instability occurs.
That critical Rayleigh number is for any Prandtl number, or is there a curve?
Yes.
Oh, really?
Yes. Yes. So this value here is for nu over kappa is equal to 1, I think. I'm not 100% sure, actually. Okay, so now what I want to do is I want to tell you about I want to end by telling you about the qualitative picture of the phase diagram. So what is the basic idea? So the basic idea is that the instability is for Rayleigh numbers such that the real part of omega of Q, wave number, and the Rayleigh number is equal to 0. So this is called the neutral stability curve. So let me explain what I mean by that. So let's suppose I draw up here. You tell me a Q vector, the wave number. I called it K before. But now I switch to Q. Why did I switch to Q? Because it's a dimensionless variable. It doesn't matter. So this is the wave number. And then this here is the control parameter, which I'll call in my notes R Rayleigh Rn of Q. So depending on Q, I have a Rayleigh number where the fluid is stable. So below here, this is the critical Rayleigh number, Rayleigh of C. So below this point here, the fluid is stable. And then above here, it is unstable, but we don't know to what. So what is the strategy? So we want to find out what happens above the critical Rayleigh number. So the only thing that we know how to do for these complicated nonlinear problems is we guess solutions. Okay. So that's terrible. Okay. We can either guess them, or we can do a computer simulation, look at the simulation and say, ah, this is probably what it is. So here's an example. You might have stripes. So a stripe would be the velocity field as a function of z is some amplitude, some u as a function of q in the xy plane times e to the I q naught x plus its complex conjugate. That would be an example of a stripe. Okay, it would look something like this. Okay, fluid is going up and down. The velocity field has some z dependence, which is determined by this function on the outside, and then in the xy plane, it's just a sine wave in the x direction, but nothing in the y direction. Okay, so that would be one possible solution. Okay, you could do squares. So you could say u of x is equal to a u q of z, so the amplitude in the z direction, and then e to the I q x plus e to the I q y y plus the complex conjugate. So that would be a wave in the x direction, a wave in the y direction, and they will produce, depending on what the q values are, some wave. Okay, so that would be another thing. And you can imagine making hexagons and things like this. So you can do many more of these things. And then the question is, are these observed? So the answer is, I don't know. Let's try the only thing that we know how to do, which is linear stability analysis. So what you do is you take these states, you plug them in to the equations of motion. You find out the values of the wave numbers that can satisfy those states and can make the system stationary. Then you look at their stability. Of course, you can't do this analytically because it's way, way too complicated. So you have to do it numerically. Okay, if you're going to do it numerically, you might say, well, why bother? But you could just do a computer simulation. So that's a good point. You might want to do that. But analytically, you learn some insight. So because you learn what are the ways that these different modes become unstable. So you try linear stability analysis, and then you have to go and do the whole thing again, but with now a linear operator, which is an operator not about the ground state, but about some periodic states, like one of these states that I've shown you here. So this, because you're now doing the stability analysis about a state that is supposedly the outcome of a instability itself, these are called secondary instabilities. And you can imagine that you might keep doing this forever, right? Which is possibly true. So what you would do is do the following. You might say, let's make a base state, which is, I'll call, say, u with some wave vector u, which is some function uq is a function of x, y, and z. And then I'm going to look at perturbations. So notice that this state is already a periodic state. This Q here is the periodicity of the pattern. Okay, it's not the wave vector, it's the periodicity of the pattern that has emerged. So then now, if you're going to write down perturbations, what are they going to look like? Well, they're going to have their own wave number. And I'm going to call that wave number Q. So it's not the same as K, and it's not the same as Q, little q, that is the periodicity of the pattern. This is the periodicity of the instability about the pattern state. So we're going to write it as that the perturbation is equal to u, some new thing, u1 of x perpendicular and then z, and then e to the I q dot x perpendicular times e to the omega t. But now this omega is a function of the pattern that I've got. Forget about that QC. It's a function of the pattern I've got and the instability. So the first Q is the pattern, the second Q is the instability. Okay, so if you think this is complicated, you're right. Okay, so let me give you an example of what can happen. So this is Q. This is the Rayleigh number. So Q is the wave number of the pattern. So now let me draw the phase diagram. So here is the critical Rayleigh number. So below this, the uniform state is stable. That's what we found. Then it turns out that there is a neutral stability curve, which is the thing I talked about before. So now in here, the uniform state is unstable. And so inside here, inside this region, you would think there would be a pattern. There is, but not where you think it might be. So in this regime, this yellow one, this is where you have a stable pattern. And this pattern is periodic. In this regime over here, the periodic pattern is unstable. In here and in here. Okay, so what is it unstable to? So you can work it out. So there's on this line here, this is called the Busse balloon, after Mr. Busse, who first did this analysis heroically in the 1970s. So along this line here, we have what's called the zigzag instability. What does the zigzag instability look like? Well, remember these periodic patterns are rolls. Okay, so in here, these are patterns that look like this. Okay, so in the zigzag instability, the way they go unstable is by making zigzags like that. So that's another instability. And then over here, on the left-hand side, on the right-hand side, you have what's called the Eckhouse instability. And so in the Eckhouse instability, what happens is it looks like this. Okay, so this is the wavelength changes. So there's different ways that all these patterns can go unstable, and we can analyze these things using the method that I've mentioned to you. Okay, so we come to the end of the hour, so I'm going to stop here. What I'd hoped to do, what I planned to do, except until I realized that Monday was a holiday, was show you what is the equation that describes the instability of these patterns. Okay, and so I'll see if I can squeeze that in on next Monday's lecture, because it's interesting. The equation that you get that describes this is actually the Ginzburg-Landau equations that we've seen in superconductivity and superfluidity and everything. Okay, it's the same equations. Okay, so it's very cool that happens. So I have a very quick way to show you that. So it won't take me very long to explain that to you. Very quick and dirty way to derive it. The best way to derive it is by renormalization group, which is a lot more complicated, but you can do it in very quickly and physically, and that's what we'll do next time. So that's why I'll end today's lecture. Okay. Any questions about today's lecture? Okay. Yeah.
So even just with a linear stability analysis, this seems very much like a phase transition, right? You have some critical value and your behavior changes dramatically.
It does look like a phase transition.
Right.
Yeah.
So when
but it's not.
Okay. So well, like for example, when we studied phase transitions, we had to invest some effort into saying, phase transitions are non-analytic. Where does the non-analyticity come from? Do we have non-analyticity here? Do we have to go through the same arguments of trying to understand where it comes from? Is that a mystery here?
So the answer to the question is it's kind of like a phase transition. So these transitions, at least the way I've described them, these are bifurcations, not phase transitions. The reason is that the phase transitions are from statistical mechanics. So they're in thermal equilibrium. Everything we did last quarter on phase transitions was in thermal equilibrium. We used the Boltzmann distribution. We used the normalization group to study the non-analyticities of these systems. Here, there's no thermal fluctuations. Here, we're not in equilibrium. There's just a bunch of differential equations. So it's not technically a phase transition. You could say, well, there's thermal noise, so that could make some difference to these things. And it's true, it can. But in a very, very tiny interval of the parameter space. So most of these things do not seem to be phase transitions. Okay, all right, wait. So technically these are bifurcations. The other thing is that these systems, the way we've done it by doing these mode expansions, has reduced a very complicated partial differential equation to a set of ordinary differential equations for certain modes. Okay, so this is now the realm of dynamical systems theory, which is basically just a complicated way of solving F equals ma, but we're not solving statistical mechanics. Okay. Now let me tell you the punchline for next lectures. Okay. Okay. Even though you start off with a fluid, let's suppose I ask not what happens in convection. I take the water in the tap. I turn on the water, and the water comes out of the tap, and it comes out turbulent. Okay, and you say, "Oh, that's turbulent." Okay, can I make it come out more smoothly? So you turn the tap so it's now coming through smoothly. Okay, so that's called a laminar flow. Yeah. Turbulent flow is called a turbulent flow. Okay, the transition between laminar and turbulent is a phase transition, even though the equation is completely deterministic.
And there's no statistical mechanics, no thermal fluctuations, nothing.
There is no statistical mechanics. There's no thermal fluctuations that you put on at all. Okay, but what has happened is that the system has generated its own stochasticity, and it's a phase transition, but it's a phase transition not with an equilibrium phase transition like the Boltzmann distribution and all the things that we did last quarter. It's a non-equilibrium phase transition, a phase transition in a system that is out of equilibrium in a non-equilibrium steady state. Okay, And that phase transition, we can actually work out the normalization group theory for that. And we can predict the exponent and the critical behavior and the universal scaling functions and so on. And the paper that shows how all that works came out in Nature Physics yesterday.
Oh, congrats.
Nice.
And there'll be an article about it in UCSD School of Physical Sciences, and it should be online. It's online right now, and it'll be printed in like literally on dead trees on the June 1st issue of Nature Physics. Okay.
So just because, right, this is a case where it's a bifurcation, not a phase transition, but just because it's not stat mech doesn't mean it's not a phase transition.
It's until our work,
Okay.
nobody knew that this could happen.
Okay.
You solve the Navier-Stokes equations, and they behave like a phase transition. Now the reason, okay, it's 2:00. Anybody who wants to go home, please go home. Now I'm going to tell you the most interesting thing you've ever heard. Okay, so the Navier-Stokes equations are described by, fluid is described by Navier-Stokes equations. It's all exactly as exactly deterministic. Okay, so but it really is a phase transition, and we can demonstrate that. Okay, so how do you get a phase transition or something like that? Remember, every dynamical system, whenever you do statistical mechanics, it is after all a deterministic system. Okay, I've got a bunch of particles bouncing around in a box. You can go and program it up in Python, simulate particles bouncing around in a box. Everything is deterministic. You're just solving Newton's equations, and you will see, you can measure the laws of thermodynamics coming out of an equilibrium, out of a dynamical system with no noise added. Okay, in statistical mechanics, where the temperature comes from, where the thermal fluctuations come from, it does come from the actual dynamics. Okay, now, you guys have not had statistical mechanics from me. If I was teaching statistical mechanics, I would tell you what is the proper explanation for where you get the Boltzmann distribution in statistical mechanics. But ultimately, every system is deterministic in some sense. Even the Schrödinger equation is deterministic. Okay, right. So what happens here? Okay, this is really where it gets really bizarre. If you look very close to the laminar turbulence transition in a pipe, you see that right at that point, just like here in today's lecture, we saw that there is one mode, where did I draw it? One mode here that just becomes critical. Okay? So very close to that point, you look at what are the critical modes. And what you see is that there are modes that are turbulent, and there's one mode that is generated by the turbulence, and there's a mode that is going around the pipe in this azimuthal direction, and that mode is an emergent mode generated by the turbulence. Okay, so that can happen. That there's nothing. That's just solving Navier-Stokes equations on a computer. That mode, however, is generated by the turbulence, but it rotates the turbulence and shears it and makes it more isotropic. So the turbulence creates the mode, and the mode then destroys the turbulence. Okay, so there's an activation and an inhibition. So what happens is these two modes behave, something activates, something inhibits. Here's another example of something that activates and something inhibits. Predator and prey in an ecosystem. I have a wolf, I have a sheep. Wolves eat sheep. Okay, the sheep grow, they make more babies, and the wolves say, there's plenty of food to eat, let's go and eat the sheep. So the wolves go and eat the sheep. Then the sheep population goes down. Now the wolves starve, so the wolf population goes down. Now there's not too many wolves around, so the sheep population goes back up. And so you get these oscillations. Okay, the sheep activate the wolf population. Without the sheep, you wouldn't get wolves. But the wolf population inhibits the sheep population. So you have activator inhibitor. That same dynamics happens at the onset of turbulence. Okay, so now you say, okay, fine. So if I'm going to make a guess, I would guess that the turbulence transition is something like the wolf-sheep behavior in an ecosystem. So now you try to write it down. And this is where it gets truly bizarre, okay? Because you cannot write a deterministic description of the story that I just told you with the wolves and the sheep. Okay, it is inherently stochastic. There is no sensible deterministic description of that. I'll tell you about that next time. Okay, so what it turns out to be is that it has to be described stochastically, and the reason why is related to things that happen in quantum field theory called anomalies, which are what happens in high energy physics and things like this. There are stochastic analogs of quantum anomalies, and they tell you that in the stochastic case, there are some problems where there is no deterministic limit, just like there are some quantum problems where there is no classical limit. Okay, once that happens, you have a stochastic theory, an intrinsically stochastic description of the system. And when you write that down in quantum field theory, and then you simplify that and look at the phase transitions of that quantum field theory, it maps into a quantum field theory that was discovered in high energy physics about 40 years ago called Reggian field theory. And that Reggian field theory is a field theory, except it's not a field theory because it actually violates unitarity. It turns out to be a theory of Markov processes. And when you work out that theory, it turns out to be the same thing as what happens when water drips through the coffee percolator in your house when you make your coffee at breakfast time. Okay, so this is nuts, and that behavior of fluid dripping through coffee granules is a phase transition called directed percolation. I'll tell you about that next time. Okay, and so the turbulence transition is this directed percolation transition. It behaves like an ecosystem, which behaves like coffee going through coffee granules. And so you've got a fluid, which is continuum and deterministic, behaving like a bunch of particles on a lattice, being stochastic. And yet, everything behaves exactly the same way. This is the most extreme example of universality as I know about. Remember last quarter, we talked about the universality between the liquid gas transition and the magnetic transition. Okay, we talked about that and we understood it in terms of symmetry. This is that on steroids. There are multiple transitions between these different descriptions of the system, these levels of description, which then lead to predictions that you can then verify experimentally.
And yeah, that is all bizarre, truly bizarre.
It's really insane, right?
It's, if I'm understanding correctly, an important point about it being a phase transition and not a bifurcation is the fact that for all of these different classes or all these different systems in this universality class, you cannot have a deterministic description. You need to have a stochastic description emerge.
Phase transitions are inherently stochastic, yes, because they have thermal fluctuations. And as we saw last quarter, it's thermal fluctuations that cause the system to behave in ways that are so non-analytic that you need the normalization group to capture the non-analyticity.
But like if you had a system where mean field theory applied, like superconductivity,
yes,
there's no fluctuations, but you would still say it's a phase transition.
Yes, you would, because it's the mean field description of a phase transition.
Right.
So you can think of bifurcation theory as being it's just mean field theory, and some people think of it like that. But they are slightly different for the reasons that I said. One is an approximation to something that is inherently stochastic. One is not an approximation to something which is dynamical.
I see.
And deterministic. So very good question. I'm sorry that my answer was insane. Okay.
Much less maybe.
By the way, this is the office hour because I forgot to announce that my office hour is cancelled today. So I have to go home. So if anybody wants to talk to me, it has to be on Zoom. Okay, and you can just send me a message through Teams. Okay.
Very interesting points that we just talked about.
Yeah.
It's very exciting and so enlightening. I was wondering, kind of a little bit more pedestrian, back when we were looking at.
Well, why does
the
milk cost
sudden-
$3 a
Yeah,
carton?
no. When we were looking at the sudden change from a system that's above TC to below TC, where we suddenly have an order parameter that going to shift to this new value, and it's suddenly done, it's quenched immediately. Then there's a force that's moving the state into this new
Mhm.
new local minimum, this global minimum. When I look at that dynamically, it should overshoot, right?
Yes,
And so then you're going to have kind of like a coherently kind of driven.
well, it can.
mode.
It will.
Yeah.
Remember, we didn't write down the equations of motion for this.
Right.
So let me go back to my figure here. So if we go back to this figure, and you say, okay, I want to make a dynamical description of this, I would write down an equation of motion which would include viscous damping.
Exactly, right.
And when you do that, then it'll overshoot and then oscillate back and forth, and then it'll just fluctuate and so on.
So in systems where there isn't very much damping, we make, for example, if I take a magnet, if I
Yeah.
take a system that's a magnet,
Yes.
and suddenly freeze it.
Yes, you can have
magnetization may oscillate.
magnetization waves and things like that.
Just checking.
Okay, all right.
And is it-
Bye. Yep.
sorry, is it fair to say that, so when I have, for example, a magnet transition, like the KC that we have is the typical size of domain or bubbles, let's say, which are formed.
No.
by magnetic transitions?
It's not, because the domain walls are that is the size of a pattern. Okay, but then if you want to know, well, what is the size of domains, so then you have to solve for the like in a magnet, the domain walls are, you've got one region of magnetization here pointing one direction, one region over here pointing another direction. So the size of the domains is determined by the non-equilibrium dynamics of how the system is relaxing to this equilibrium. And it will do that in a way that depends on its behavior. Domain walls are non-equilibrium. The system has just evolved, it's formed a domain over here, a domain over here. They may have the same length scale, the same K, but the size of the domain will then just grow and grow until they run into each other. And I think, I don't know if you probably didn't come to the beginning lecture of the course, but in the beginning lectures we talked about this process of phase ordering and things like this. So the domain size and the pattern size the wavelength are very different quantities. Did I answer your question?
Yes.
Another question.
Yes,
the,
Jim.
about like the phase diagram. My understanding is if you change the Rayleigh number and the wavelengths of the perturbation, and you get different behaviors of the system. So, so what do we see if the pattern is unstable for a system?
Well, the pattern will go unstable in some particular way, and then will break up into some other pattern. For example, I don't have a picture here of the phase diagram of convection, but I can tell you that you form hexagons, and then they may form rolls, and they may be wavy rolls, then they may be wavy rolls with hexagons on top, or something like this, and then eventually they'll become turbulent. So there's a whole sequence of patterns that they go through, and one can't even really enumerate them. All you can do in those situations is just do a computer simulation, and then you can ask, okay, well, let's go and look at what happens when the thing is super turbulent. Okay, and then you can ask, how does the heat transfer scale with the Rayleigh number as I go to asymptotically large turbulence? Rayleigh numbers of 10 to the 12, 10 to the 13, 10 to the 14. You can do those in a laboratory, and you can measure how the heat transport scales with the Rayleigh number. We have theories that try to predict what's going on. There isn't any agreement about which theory is correct or not. The theories yield very similar predictions, but they're quite different in their assumptions, and the people who are involved in those theories are arguing very vociferously about them. So, and then once you have a turbulent state, how do you describe it? None of the ways that I've talked about here to describe turbulence are applicable. So all you can do is the very easy thing where something is spatially uniform, then it starts to form a pattern, and then the pattern may then go unstable. You can maybe understand that, like the zigzag instability or the Eckhouse. Beyond that, it's just like very complicated. But the basic tools that we have to analyze these things are very crude. We can't do much more than linear stability analysis, and then the one other thing, which I'll tell you about next time, weakly nonlinear analysis. Other than that, yeah.
Can you think about this process of the instability, and then that forms something, that more instabilities in terms of bifurcations? Can you think about it as a first bifurcation, and then more, like in the logistic map, you get multiple series of bifurcations. Kind of, but not as interesting as, remember, after one lecture, I gave you a second lecture about levels of description and fractional quantum Hall effect. Yes.
And how topological defects can form like vortex lines in a superconductor or superfluid, can form a lattice, and then that lattice can have dislocations in the lattice, and then those dislocations can then act like vortex lines, and so on and so forth. And so it's topological defects built on topological defects built on topological defects with their own different levels of condensation and topological defects.
Right.
And so it's not quite as interesting as that, but it's a similar kind of thing.
I'm surprised dimensionality doesn't.
Dimensionality does matter. Dimensionality does matter in all of this. Yep. So those details are important. You're exactly right.
I remember something is like in 2D, you can't form turbulence based, and sort of a topological intuitive reason is that you can't form knots, like vortex lines in a fluid. You can't form knots with each other. And so what happens is all your vortices end up clumping up. And in simulations in 2D, your sort of steady state at the end is always just kind of one big vortex.
That's true, but it's not true that you can't have turbulence in 2D.
Interesting.
Okay, so what can happen in 2D is that you can have a cascade of energy to large scales, kind of like you described, but you also have a cascade of angular momentum, so more precisely entropy, angular vorticity squared, to small scales. So you have two cascades, one going in the up direction, one going in the down direction. And you can create two-dimensional turbulent flows, and we've done it, and you can work out the theory of those and so on.
Right. Okay. I think what I was thinking of is that the Kolmogorov cascade gets reversed, but then you still have a different cascade.
Yes. Yeah. A batch accretion cascade. Yep.
Do you have time for another question?
Sure.
This is his awesome.
So just to actually this slide here on the left, just to maybe clarify this point, hammer it home for myself. The reason why susceptibility is related to stability is because susceptibility is the second derivative of the free energy.
Yes.
And the second derivative tells you about the stability properties of a function.
It does, but think about it in a different way. Okay. Think about compressibility. Okay, so let's suppose I've got some material fluid, and I compress it. What I expect is that its compressibility will be positive. The compressibility is minus dV by dP. It tells you how if you apply a force pushing inwards, how the volume decreases. Okay, and that had better be positive with a minus sign there, so that as you try to make its volume decrease, the pressure increases. Now imagine material where as I pushed it and squished it, its pressure went down. Then it would be, you get a black hole, okay? That would be unstable. That would have a compressibility that was negative, okay? Now the same thing is true here, but with M replaced by H. So what I expect is that as I apply an external magnetic field, a material becomes more
Right.
magnetic.
Right.
Okay. If it becomes less magnetic, then
Yeah, it's just horribly unstable.
horribly unstable. Or heat capacity,
Mhm.
right? I heat something up, the energy had better increase.
Okay.
Okay. So this is yes, this is d2f by dh squared.
Right.
But and so you can say that's negative, but you can say, well, that's like this negative slope here, except it isn't,
Mhm.
because this is d2f by dh squared, but this is psi of n.
Yeah.
But it turns out that they are related to each other
I see.
by the inverse.
So it's
This is something I explained to you in our office hour about why it was that mean field theory, Landau theory, could tell you about the fluctuations at a
right.
phase transition,
Right.
right?
So it's always something physical. There's always a physical reason for these things, you know. Let's see.
Okay. So did I give you the physical reason?
Yes. No, that was great. That was excellent.
Okay. All right. Thanks for the great questions. I'm going to turn on. Hey, anybody on Zoom? You have any questions? Anybody still there? Nope, they've all gone. Okay.